Good morning. I hope you're doing well. I, for one, am doing quite well. Yeah, it was a good week this week. Lots of interesting things happened. Some, I don't know, slowish things that needed to be done eventually, and I finally bit the bullet and actually did them. But definitely some very exciting things, and I'm very keen to show you what's up. What is the hap? So the big question of this week is, can Jugglebot catch a tracked ball? And is 50 milliseconds actually too tight? So a big part of, throughout the last week, well, during last week's stream, I mentioned that I wanted to try to get the hand to catch passively. And this is something that we've explored a little while ago, a couple months ago. And we kind of moved away from that because getting the gains to be tuned perfectly is quite tricky. And we found that that tuning didn't really help too much. However, using John's trajectory generator, we can get very clean throws and catches. However, my big lingering question was always, sure, that trajectory generator works really well when that generator is what's making the throw, and then it can catch really smoothly. But what if something else is making the throw? What if I'm throwing the ball to Jugglebot? Or if there's like an error, like there's a collision in the air and one of the balls has to, like its whole trajectory completely changes, and now we have to try to catch that new, that ball with the new trajectory. What then? Does the generator work as well then? And last week I made the claim that the 40 to 50 millisecond window that we have between when the ball, if the ball is falling from like 2 meters, when the ball is at the top of the hand stroke to when the ball is at the bottom of the hand stroke, that's around 40 or 50 milliseconds. It's like tens of milliseconds. And my claim last week was that that time window is too tight to reliably have the hand catch. And after the stream, I talked a little bit with John on Zulip about this, and he is of the opinion that by the time we are getting to where the project will be eventually, which is to say doing 14 balls or 7 balls in like one arm, one hand, by the time we reach that point, 50 milliseconds is going to feel like forever. Which is potentially true. Like these things the timing is very sensitive to how high we're throwing the balls. And if Jugglebot can precisely throw balls like 5 or 10 meters high, then we should have a fair bit of time. But I do take his point that like as we start increasing the number of balls, the amount of time that we have to do each step of the process is going to get smaller and smaller and smaller. And honestly, as far as the robot is concerned, as far as the computer is concerned, at least 50 milliseconds is ages. And so this has made me realize that that claim was potentially unfounded, and I didn't actually have any evidence to back my claim that 50 milliseconds is too tight. And so this week I wanted to explore if that's actually the case. So I've got some interesting things to show you. But before we get there, there's a couple other small updates that I want to get through. The first is that it is finally time to beef up some bits. So last week I mentioned that the spool that the string wraps around is starting to unwind itself from the motor, and I'll show what this looks like in the CAD in a couple minutes. But the easiest, and I explicitly mentioned last week that the long-term solution for this is to get an aluminium spool and then like Loctite it onto the motor so it can't go anywhere. And I was thinking about doing that for a little while. I'm like, yeah, cool, like that would work, but I don't really want to have to wait for that to arrive, and like putting in the order on JLC 3DP is like a bit of a hassle. But I finally decided to bite the bullet. The thing that, the straw that broke the camel's back is that I kicked and broke one of the tracker mounts, which is kind of annoying. So these tracker mounts are the ones down on the bottom of Jugglebot, and these hold the trackers that I'm using to figure out where Jugglebot is actually positioned in my room. And breaking this was kind of annoying. So this is the one that broke. It was over here, and I have now moved it over a little bit to hopefully, I don't know, move it away from the edge a little bit, so when my foot's around there, I hopefully don't hit it as often. But yeah, and you can see by the fact that this is so high off of the base, you can kind of get the impression that this part does not print very nicely. I actually don't have it open right now, but let me show you what this mount looks like. While I'm doing this, Lawless, good to see you. Sup. We are in MISC, and we have Mocap related. So this is my M6 to M4 adapter. The reason why I need this is because the trackers have an M4 thread in them, but the holes that I have in Jugglebot's base have an M6 thread. So I need to have an adapter to go between them. And the way that I was doing this before was when I'm printing these, I'm printing them with this thread in them, and that does not print nicely. It doesn't really work, at least for my printer. That thread, yeah, it always ends up like, woo, just kind of like skewing around. And so I've ended up having to like cut off like the bottom half of this thread, and it works well enough. It's in, like that's, yeah, it's in. It's not the best. So I'm not super happy with that. So I'm hoping that we can get these made out of aluminium. And I want to get 10 of these tracker mounts so that I have some spare. And also because 6 is kind of like, we could definitely afford to have more. And we should then have even greater precision of like where the base actually is in space. And at least we'll have extra ones. I also want to get 3 spools for the string. I only really need 1, but you know, backups are good. And I want to get 1 motor wrench tool, which is this tool that I showed last week that John made to help tension. I've actually got a motor here now so I can show it, so that we can actually like screw things onto this motor shaft. I can slot this in here real nicely, and that holds the motor nice and still, if I can focus. So this way we can like grab the motor and then screw whatever we want onto this shaft. The way that I was doing this before I had this tool was to just hold these little vanes with pliers, and that did not work very well. There was one motor that when I was holding it like that, my pliers kept on slipping and I was like gouging bits of metal out of these vanes, and some of those bits of metal ended up inside the motor, and now it's kind of cooked. So this tool is very nice. And to be honest, I don't really need this to be made out of metal, but I just want to try their anodizing red, and I want to see what their red looks like. Because maybe, hopefully, if it matches Jugglebot red, we can get some nice, cool red aluminium bits. Virtualize Everything says, have you tried SLI prints? SLS? I don't know what SLI is. Short answer, no. I've only tried my FDM printer. However, and to be honest, if I was paying for these parts out of my own pocket, I probably would consider some cheaper printed options. I think maybe not for the spool. For the spool, I don't want to have to mess around with this unwinding itself again, so I really want it to just be like locked onto the motor. And so anything made of metal would be fine as long as it can have a pretty tight, I think that's an M5 thread on the motor part. But thankfully, JLC 3DP they have sponsored my last video, and I'm happy to have them, and they seem to be happy to have them sponsor future videos. And interestingly, they're actually happy to just, like, even though we don't have a defined sponsorship agreement for any future video right now, like we have nothing specific, they're still happy to pay for these parts, and that's great. And the initial quote is like $260 for Australian dollars for all of these parts. And yes, I'm pretty happy to not have to pay for those myself. It's very nice. And I suspect that quote is going to go up a bit once they analyze all the threads. Yeah, because I'm a little bit curious actually. I don't know if it will be very easy to CNC this part in particular, because like this is an M4 thread in here and this is an M6 thread in here, and there's not a huge wall gap in here. I could potentially raise this up so that like this channel doesn't actually eat into here at all, so we can go like I can like bring this surface. No, well, imagine the chamfer is not there. But yeah, bring this, like thicken this part up a bit. And that could work, but I really want these to be as low as possible so that I stop kicking them. Yeah. But we'll see how that goes. Unfortunately, they are on like they've got the Lunar New Year coming up, and so I can't actually place my order yet. So these might take a while to get here, but at least it's in the works. Cool. The next thing is that the hand ODrive needed a reset. So I mentioned last week that when I was sending these like set input position commands, there was just weird stuff happening. And for example, when I was doing some testing after last week's stream, I was maxing out the current limit. It was like hitting 50 amps just trying to move the hand up like a nice smooth like sinusoidal sort of path. And I was like, this is not right. Something weird is going on here. And I tried a couple of things, but the final thing that ended up fixing all my problems was just to reset it. So yeah, if anyone out there is ever using ODrive Pros, I'm finally starting to get in my head that if weird things are happening, just reset the firmware. Just clear the configuration and reset it. And 9 times out of 10, if you've got really weird things happening, in my experience, if you've got weird things happening that you don't really understand what's going on, resetting the firmware just fixes it. So I don't really know why this happens, but it does, and this fixes it. So virtualize everything says, sorry, SLA is a file format. SLA is a print type. Yeah, SLA with like the dust and like the laser that goes over to like really precisely make things. Yeah, I would love to have one of those printers. It would be so good. I actually backed the Micron Labs one, but as I'm sure many of you probably know, that project has kind of disappeared and will probably not re-emerge in the consumer space for quite a while. So my hopes for having ready access to an SLS printer have very quickly dropped. But thankfully, now that I've got this JLC 3DP sponsorship, they seem pretty open to just pay for all the bits that I need. I'm pretty keen to just get everything made of aluminium from them, which is really handy. I'm super appreciative of them. And also, for the record, like, they don't sponsor these live streams at all. So everything that I'm saying now is just my own opinion. But yeah, I'm keen to see what how these parts turn out when they eventually get here. Okay, so now let's get into the juicy bits. Is 50 milliseconds really too tight of a window? So my thinking for how to test this is that I can set up a rig where I can drop a ball into Jugglebot, and using the motion capture cameras that I've got in my room, we can detect when that ball has been dropped, and then if we can catch that ball reliably, that's a good sign. If we can't catch that ball reliably, and if the timing just doesn't work out, then that's not a good sign. And we maybe need to tune some things to get it to make that catch. This is kind of like the easiest possible case of catching a ball that Jugglebot did not throw. At least that was my hope, is to get that sort of setup. So yes, can Jugglebot catch a dropped ball? And the high-level overview of what this sequence looks like is that we can raise the hand to roughly the top of its stroke, wait for a ball to drop, calculate when the ball will fall to the point where it needs to be caught, and then catch. Hopefully getting the hand to move so that it intercepts the ball at this point. Cool. So let's go through all these one by one and see how they work. And then I'll give you a demo. We've got a fun demo this week. And fingers crossed it works. So the first part is we have to raise the hand to the top of the stroke. And currently, if we are commanding the hand using this like set input pos command, we have to get every single data point that we want to move the hand to get it to like follow a nice trajectory. If I just tell it go to the top, then it's just going to rocket up to the top really, really, really quickly, and it's going to be a bit of a mess. That is only because I'm currently using the pass-through mode on the ODrive. I could use the filtered input pos, or whatever it's called, but I haven't been using that right now. If you have any suggestions as to whether I should or shouldn't, I'm all ears, but so far pass-through mode seems to be working pretty well. So yeah, I can't just command go right to the top because it's just going to shoot up and probably overshoot, and yeah, it'll be a bit too aggressive for my liking. I want to try to minimize the number of times that I'm getting the hand to do really aggressive movements, so I wanted a nice smooth profile for it to follow. To generate this profile, my first approach was to use a cubic polynomial where we can set that we're starting out wherever we're starting out, in this case starting at 0. We can set where we're ending up, and we can set the start and finish velocities. And this seemed good, and I was like, yeah, cool, this looks good, until when I plotted it, and I realized that because this is only a cubic polynomial and there are only 4 unknowns, we can't set what the acceleration is at the start and the end. And so there's this big jump at the start and the end. The acceleration is discontinuous. Like, we go from 0 acceleration way up to whatever this is, like 12 or something. And then at the end, we go from like -12 up to 0. And that's not inherently too bad. Like, it's not going to make the hand like jerk much, but from what I have gathered over the last, I don't know, year or two of like looking at this sort of robot control, the consensus seems to be that you want to minimize the amount of jerk, which is the amount like you want to minimize the quickness that your acceleration changes. You want your acceleration to be nice and smooth as well as your velocity and your position, because over time, if you continue jerking around this acceleration, then things will like loosen up and they'll wear out faster, yada yada. So this is no good. Well, it probably would be fine, but it's not as good as it could be. But if we go up to a quintic polynomial, so this one, let me just write on here. This one is cubic, and this one is quintic. And we can see the end result of the position is like pretty much identical. Unfortunately, when I took these screenshots, I had like scaled the images a little bit differently. So yeah, the x-axis is scaled a bit weirdly, but they are like, it's the same motion. It's same start, same end, everything else. And yeah, you can see that the position looks pretty much identical by my eye. Like there's very little change there. But if we look at the velocity, then we can see it starts to change here. So now we still have 0 velocity at the start and end, but now we also have 0 acceleration at the start and end. So it's a little bit smoother. And this works super nicely. So I now have in my code a generator to generate this profile, and I can tell it where I want to start, where I want to end, and how long I want this profile to take. Right now I've got it set to 2 seconds, and that always results in a really nice, slow, smooth motion, which you will see in a couple minutes. Basic Flash Cube says, I just watched Elon catch a rocket. Now let's catch some balls. Yes. I think the rocket catching themselves is a little bit more impressive than this, but we'll get there. I reckon in a couple of years, Elon's going to be jealous. Maybe. Cool. So yeah, getting the hand to move to the top is fairly straightforward once we get this profile done. Actually, there's one interesting thing that I want to mention about this. When I was going through this, I wanted to... So the general setup here is, let me show you my working out. We have this this polynomial here for the position, and we've got these 5 unknowns, so A, B, C, D, E, and F. Oh, sorry, 6 unknowns. And we want to basically figure out what those constants are. So we need to figure out what A, B, C, D, E, and F are. And I wanted to go through and just like verify that I still remember how to do this, and also that I can just check what ChatGPT tells me what the answer is. And I found this really interesting. So I took, I don't know, a little while to write all this out. Just like the sheer number of like symbols that you need to write out it takes some time. And of course there's like, in this case, you're solving 3 simultaneous equations, which I just got Wolfram Alpha to do. So I did kind of cheat a little bit. But interestingly, GitHub Copilot, when I was going through, I was like, originally we had the cubic one. And I'm like, no, I want to change this to a quintic one. And I'm just like tabbing through, and it did all of these coefficients like perfectly. It was just like boop, boop, boop. So honestly, like if you're not super savvy with this sort of stuff and you don't really know how to do it, obviously like you got to make sure that you, I don't know. I would definitely advise plotting these things before you get like any actual physical system to do them. But it just did it straight away. It was like 5 seconds of just hitting tab, and then the answer was there versus like 20 minutes of me sitting down writing it all out, and then also still cheating with Wolfram Alpha. So yeah, it's it's pretty good. It's getting good. Granted, this is the sort of thing that I imagine there is a shitload of training data on. Like this is the sort of thing that's been done so many times before, but still, it was really good. I was very impressed. Or fireworks at the end. I've got some thoughts on fireworks, but we'll leave them for another time, I think. Fireworks versus Jugglebot, I should say. So the next step of this process is to wait for the ball to drop. So we've got the ball held up above Jugglebot in a little gripper thing, which I'll show in a sec. And we need to wait for when this drops. If we have the hand move before the ball is dropped, it's not going to do anything. And if the hand moves way after, it's not going to work. We want to get it exactly as the ball drops. So what I'm doing here is I have a DQ of, in this case, I've set it to 300 frames to save, which is about a second. Well, it is exactly a second and a half of data. And we've got a subscription to our Mocap data so that as this data comes through, we basically just maintain the last second and a half of data, of frames. I've mentioned a couple times in the past that this Mocap system is a little bit annoying to work with when there's multiple markers around the place and like keeping track of which marker is which, especially when you get occlusions and one marker drops out of the frame. That can be a little bit annoying. So right now, just for the sake of testing things out, I am just making the assumption that there's only going to be one unlabeled marker. Unlabeled meaning in the motion capture program, I have not told it that this is like a specific object. For example, right now I have 6 markers on the base, and those are labeled markers. And let me show you what that looks like. I've actually got to open this up. This software was taking up too much RAM for me to edit my thumbnail for this video, so I had to close it. So yeah, we can see this is our software, and this is... I don't like these controls. They really need to make this compatible with the Space Mouse. So yeah, this is our base, and we've got these 6 labeled markers. And there's one unlabeled marker, which is the ball, which is currently being held in the gripper, which I'll show shortly. Yep. Cool. Yeah, so we're basically just maintaining that list, and that's fairly straightforward. But that doesn't actually tell us when the ball has dropped. So the way that I'm doing that is with this method here. And you can spend as much... Oh, I think it's worth going through this actually. So what we're doing is... This is run... if I can remember, this is a run on a... it's in like a loop where when we are at the stage of this process, like the hand is raised up, we are now waiting for the ball to drop. This just keeps looping through. And what we're doing is we make sure that we have at least 2 coordinates to compare, because if we don't, then we can't tell if the ball has moved at all. But once we do have more than 2, then we look at the first of our saved frames, so the data from a second and a half ago, and then we look at the most recent data, and we say, has the ball moved down by more than the threshold? In this screenshot, it was 4 millimeters. I've now changed it to just 2 millimeters, so it's a little bit more sensitive. And yeah, so then once we detect that the ball has moved by more than that threshold, then we can say, yep, the ball has dropped. We get the time that the ball has dropped in ROS time, which is important. And we also figure out how high the ball is dropping from. Because if the ball is only like 10 centimeters above the hand, then we're going to need a different catch profile, like trajectory, than if the ball was dropped from like 2 meters above the hand. So we need to get that height as well. For reference, to get this ball Z coordinate at top of stroke, what I did is I put the ball in the hand, moved it to that top point, and then just like echoed the mocap data topic and just looked at what it was sitting at. So I looked at like the Z coordinate of where that ball is at the top of that stroke, and then we know what that coordinate is in like millimeters. There was a whole lot of like going back and forth between the code and the mocap to get this working, but it's decent now. And yeah, so after this, once this is done, once the ball has detected that once the system has detected the ball has moved down by more than the threshold, we know when the ball was dropped, how high it was dropped from, and also the fact that it has been dropped. The next step is to calculate when the ball will fall to the catch point. Now this is where things start to get a little bit funny, because we don't want to catch the ball right at the top of the stroke. The whole like idea that I'm testing here is that we can use a pre-generated trajectory that does some amount of velocity matching to catch the ball. And this is what that catch profile looks like. So we're starting at near the top of the trajectory, we're going down to the bottom of the trajectory, and what we want to have happen is we want the ball to be caught when the hand is at this point in here with this velocity. So this velocity is calculated as being some fraction of the velocity that the ball will have when it's coming in. If we wanted to do like full velocity matching so that the hand and the ball are like perfectly coming in to touch each other, we would want this to be like that ratio to be like 1, so that this velocity is exactly the velocity of the ball. Of course, then they wouldn't actually meet each other, so maybe we'd have to do like 0.95 or something to get them real close. Right now, that's set to 80%, so this velocity here, in revolutions per second, is 80% of the velocity of the ball coming in, yeah, so that it can land fairly smoothly. So we don't want the ball to touch the hand up here, we want the ball to touch the hand here. Thankfully, with John's trajectory generator, it's fairly easy to spit out we kind of know, as like part of the calculation process, we know what this position is, where the hand is at that catch point, and we also know what this time is. So the time when the hand is at that catch point. Then we want to make sure that when the ball is coming in, it comes in here. So what I mean by this is the ball is going to have some trajectory like this, where if we've got like Z position and time, the ball's profile is going to look parabolic. Well, it should look parabolic. And the hand's profile is going to look like this kind of Z thing that I showed here, like this thing, but it's going to be like super condensed, because this is only 0.25 seconds. This is pretty tight. So, and we want to make sure that these line up. If I can erase this and move it over a bit. There we go. So we want to make sure that these line up perfectly at like this kind of point. It's kind of hard to draw, but hopefully you get the idea. So what we need to do is look at the time that it takes the hand to get from its start point to that catch point, and then also the amount of time that it takes the ball to get to that catch point. And here is the code to do that. So we start off with, I just realized something that might actually change this. All right, but we'll go through this. So yeah, we start off by setting the height that the ball is actually coming from, and that's taken from that, like when we check if the ball has actually dropped. We then get the trajectory of the hand, and that's going to spit out this trajectory here. Note that this is starting at 0. So this is saying the hand will start moving to catch the ball at 0 seconds. We don't want it to start at 0 seconds. We don't want it to start right now. We want it to start when it's appropriate, so that the hand is at this point when the ball is also at that point. So we need to offset that time a little bit. So this time command starts at 0, but we don't want it to be 0. We then get the time relative to the start of the catch movement that the hand will be at that catch position. So that is this time here. So in this case, it'll be like 0.9 or 0.09 seconds-ish. We then need to multiply by the linear gain to convert the units around. That's not too important for this exposition. We then calculate the time that it will take for the ball to reach that catch position. We then calculate how long, calculate when the hand needs to start moving to intercept the ball at that catch position. And then we shift all of our time commands by that amount. Finally, we put everything into ROS time, because one thing that I found, if I just converted this all into like a float and then I sent that over to the node that actually moves the hand around, there was a bit of lag between, like, for that message to be sent over. So what I'm doing now is I'm putting everything into ROS time. So I'm saying in ROS time, we want the hand to start moving, I don't know, at like 15 seconds from the start of the node running. This is all in like the, what is it, like UTC time, when like it starts in like 1970. So like all these numbers are like super, super big, and it makes it kind of annoying to compare them very easily, because like the first like 7 digits are all exactly the same. But anyway, we're putting it into that time so that all of these nodes are like in agreement, and that way it's like fixed. Once we send it off, there's no, even if latency occurs in the network of like sending that message over, that latency doesn't matter, because the node that's actually moving the hand will say, yep, cool, in ROS time, I need to start moving the hand now. And if there's like, in the extreme case of like a heap of latency, then we will already be like halfway through the trajectory before it starts moving, and then it will just try to catch up, which may have mixed results. Yeah. I probably should put a check in there to say like, hey, if the first point of the trajectory is past the current, is like before the current time, then like raise an error and be like, hey, there was a lot of lag, like something weird is going on. I don't have that in place right now. But I could, in theory. Yeah. So, the last step is catch. And does the catch work? Let's find out. So let's go to, nope, this view. Yeah, so we can see we've got Jugglebot down the bottom. We've got my little gripper up the top here. The ball is already in the gripper, ready to go. And you can also see my my screen here, which I can make a bit bigger so it's a bit higher quality. All right, so let's start things up. So we can run the launch file, which will start up the robot. I've already run everything through its homing sequence in without having unplugged all the cables, so we don't need to home or anything, which is actually probably pretty useful in this case because it means that the hand will not move at all. During that homing process, the platform tends to, it by definition does move a bit, and because of I've just got this the gripper thing positioned on a tripod, getting that positioned straight took quite a while. And I'm a little bit wary that if I had to go through that homing sequence again and again, it might actually move the hand just enough to cause issues. Because when I'm doing this drop testing, I'm not actually using the platform at all. I'm just all the legs are just off, just to make it easier. Yeah, so I'm very glad, once again, that I have automated this startup process to not have to go through everything if it's already done it. Do a countdown. I will do a countdown, but I'm using this microphone now, and I've got to stand over there to drop the ball, so you might not be able to hear it. But yeah, so this is all, it's on, the robot is just kind of waiting in idle, and now we can call the prime hand service, and this will raise the hand up. It's now sitting there, ready to go, and we can see that we are, I don't know if you can read that text very well, but we are waiting for the ball to drop. And so now I can go over, and I'll do a countdown, and hopefully you can hear it. 3, 2, 1. Let's try one more time. So as I mentioned, getting this tripod in the right spot took a while, and I think when I was lowering the black screen to get a nice backdrop, it actually bumped the tripod a little bit. So it's not perfectly lined up, and I'll show you in a second what my dropper actually looks like, but the short story is that it's not great. So it tends to not drop the ball super reliably, which is a bit of a problem. So try one more time and see what we see. That was close. So, as you've seen, it's not perfect, and actually, I want to get a good one on the stream. So let me try one more time. In my testing before, this had about a 50% success rate of perfect clean catch. So we should be due for one now. Right on cue. Yeah, so you can see when it works, it's clean and very nice. Cool, so let me just turn this off so we don't have the fan noise. And I've got some things to say about this. The first is that I've added this into, let's just go on to, we don't need to see Jugglebot anymore. Yeah. Yeah, I've added this into my plot juggler UI thing, so we can actually analyze what has happened here. Now, annoyingly, if we just add the Z position of the ball when it's being tracked, it's in a completely different unit to the position estimate of the hand, and so we have this, it's not scaled nicely at all. Also, I did have a look around, and as far as I'm aware, there's no way to make this UI larger, so yeah, if you're on mobile, I don't know, sorry. Watch it on your TV, apparently most of my viewers do, which is kind of weird to think about. Yeah, so what I've done is so that we can actually see how close this timing actually is. By the way, this is a recording from before, this is not, I'll put on the recording that we just did then, but right now I just want to show this one. Yeah, so to get these to overlay nicely so that we can actually see what's going on, I've made this tab where I've scaled them. So let's, yeah, get rid of that. How do I move that one? Yeah. Yeah, so in this plot, the orange line is the hand position, and we can see that the hand moves extremely quickly. This is what I'm saying. We only have, what is this? You can see down here is the time. So this is 25.454 up to 25.6. So that's yeah, I mean, we saw the plot before. It was like 250 milliseconds to go from the top to the bottom. That's very, very fast movement. And then the green line is the position of the ball. Now, of course, this is not actually scaled correctly because the ball is actually starting like way higher than the hand is, but you know, this gives some idea of how close these things are. I only actually, to be honest, I only actually got this working last night, so this is all the very last, like the last like 10% of all this is kind of hacked together a bit. And you'll see what I mean by that a bit more in a sec. But we can see with this recording, as we can see, was a nice, clean, crisp. The ball went like perfectly into the hand. Now, one thing I do want to set up with this is to get my slow motion camera so that we can view how close this actually is and at what point the ball actually enters. Because here it looks like the ball only gets into the hand like right towards the end here. So like maybe like right where this red line is here, which is pretty far through. We should be seeing it enter halfway through. So this catch seemed a little bit late, but it was still smooth. But I don't want to infer too much from this plot because the scaling is all messed up. Basic Flash Cube says that ball seems lightweight. Maybe take air drag into account when calculating catch time. That's not a terrible, like it is. You're probably right that it's worth doing that calculation just to see what order of magnitude the air drag is actually going to be, because you are right. Like these balls are very light. They're only 71 grams, so they're definitely the lightest balls that I own. And you're right, that is potentially worth considering. I'll have a look at that later today. I'll see what order of magnitude we expect that air drag to be. I suspect it's probably not a lot, especially for this drop. This is only dropping like, I mean, the recording will tell us. Here we go. It dropped, 500 millimeters, like half a meter. So it's not a big drop. But you're right that it's worth considering. So this plot, this one looks really good, but let's have a look at the data that we just collected then. You can see, look how many runs I've done over the last day. So many sessions. Loading. All right. Okay, I'm going to have to rescale this to make it nice. Yeah, this looks a bit weird. All right, so let's just zoom in on the last one. Actually, that looks pretty good. So that was the last one that did catch, and we can see that same sort of thing. It only landed right at the end. Of course, we won't actually know for sure when it landed until we. We won't actually know for sure until I get the slow motion camera to watch this, so we can actually visually see when the ball is landing. But this is still a good rough idea. But let's have a look at one of the earlier ones where it did not catch. Yeah, so this one looks like, so what have we got again? The ball is green, orange is the hand. This one looks like the ball dropped, where did that go? Yeah, this one looks like the ball dropped way too late. Like it landed very late. Although, I don't remember if it was the first or the second one here where the ball actually hit the top of the hand and kind of went off to the side. So that definitely stuffed the data up a little bit. I think this one it did not hit, but we can see like it's too late. Yeah, there's lots of interesting analysis to do here, and I need to figure out a way to get this to scale every single time reliably so that it like actually fits nicely. But because what I really want to have is like that plot that I showed before, where like the ball has this nice parabola and the hand has this like S curve, then they should meet perfectly nicely. But I need to do some work on getting that scaling to work. Now, so Basic Flash Cube says, why not use real juggle balls? They bounce way less when catching. These are real juggle balls. They're called Russian balls. And these ones are just covered in my retroreflective tape so the cameras can see them, but this is what they look like normally. And to show you what they are basically like play pit balls as far as I can tell, but they're filled with like quartz sand so that they behave very weirdly. But these are actually a really common ball for like professional jugglers to use. And I can kind of see why. I don't vibe them myself. I find them a bit weird. Maybe if I had smaller ones that'd be good, but at least these ones, I don't know if I like the sand. or whatever it is on the inside. But it basically means that they just like drop. Like when they land, they just like stay still. And that is super useful for Jugglebot because it means that when the ball gets into the hand, it just like stays in. So much more reliably than other balls that I have, which are a bit more solid and they don't have this like sand in them. They tend to bounce actually more than what these balls do. I do kind of wish that these were a bit heavier. If I had like lead sand or some sort of like really heavy powder in here, I think that would be the best because Jugglebot doesn't really care too much about the weight of these and it was working fine with my other heavier balls. So I think these could definitely afford to be a bit heavier. But I think that having the really low center of gravity is actually super helpful for Jugglebot. Yeah, so I would be hesitant to just like fill them up with more sand as like a way to make them heavier. Yeah. Yeah, so one problem with the system that I've just shown is that it's not always, the timing is not always perfect, as you've seen. And if anyone was really paying attention in that demo, and if you were looking at the code that I was showing off to the side, which one are we on? 6? Yeah. Then you'll see, actually I'll do it on here because it'll be a bit clearer. You will see that I have not, the screenshot that I was showing before of what this getting the trajectory is not exactly what the code actually is. So everything is all the same, going through until we get to, dirty offset. No one likes a dirty offset. So everything is all identical except for when we get to the point where we shift the time commands, I'm also adding in this dirty offset. And of course the reason I'm calling it a dirty offset is because this is just a hard-coded value that I experimentally calculated by doing the run once. So initially, when I was doing this, I don't want to have to boot everything up again. But when I was doing this initially without that offset, what would happen is I will show you. I'll show you. Just for the sake of science. And we can see maybe it will actually work. So let's just make offset 0. 0.0. Cool. And now let's do another run. And you will see what happens when we don't have this in here. You can probably predict what's going to happen given that I am subtracting this offset from the time. But now we can actually see for reals. Alright, so let me put the ball back in. And we can prime the hand. And now it's ready for me to drop it. That's no good, is it? Yeah, so that was what was always happening when I did not have that offset. So the ball lands in, and then the system goes, oh, the ball's falling, and then it starts to move. And I don't know why that's happening. So I've got this set up to log some of the more interesting times. So we've got like how long it takes for the hand to get from its start position to the catch, which is a very brief 90 milliseconds. Then we've got the time for the catch to happen from when the ball is dropped. And then we've got how long do we need to wait before we start moving. So this time to start moving is just going to be the time it takes for the ball to get from the drop to where it's being caught, minus the time it takes for the hand to go from the top to where it's catching. And we can see the trajectory generating, that whole process of doing all of that stuff only takes less than 8 milliseconds. So that's not really a cause for concern as far as I'm concerned, for right now at least. But for some reason, there's a massive lag in here. And to show you the way that I like calculated that that offset is by taking in the data of a run that was very similar to that one. And if the Jetson will not be so slow, I can pull in our data for the run that we just did. And let's get rid of this because it's stuffing up our scaling. So we can see, if we zoom in, if I can remember how to do these controls, let's go in a bit further. We can see that there's a dip here. So this is where the ball actually hits. So this velocity, this top plot is the position, then we've got velocity, and then we've got the currents. We can see there's a dip here. So the ball has hit here at 30.484 seconds, and then it should have been caught here at 30.821. So I basically just took this 30.821 minus 30.494, and in this case it would be about 400 milliseconds, which is pretty close to what I had before, 373. Yes, so annoyingly, that 400 milliseconds is not any of these times from here. So I was thinking that like maybe I've just like stuffed up my math a bit and we need to use a different, like I've just miscalculated what that offset is, but I'm not sure that that's the case. And to be honest, as I said, I only got this working like maybe 15 hours ago, so I haven't had enough time to like properly investigate what's actually happening here, but something weird is happening. I'm fairly certain it's not any latency issues because this is all being published in ROS time. Yeah, my suspicion is that I've just like cooked my calculation of like what my offsets need to do, or what the offsets need to be, but to be honest, I'm not certain. So yeah, if anyone's got any thoughts, then I'm all ears. But yes, so right now, the way I'm feeling about this is that I don't feel that I have like fully exhausted this test apparatus at all yet. I've definitely still got a bit of work to do to really feel confident that I've given this its best shot. But right now, like I don't know, first surface level thought is that it's not a good sign. I definitely want the system I want Jugglebot to be able to catch any ball that I throw to it and to be able to perfectly receive it. Which, in my mind, if we don't do this like calculated trajectory approach where we're calculating exactly how we need to move to receive that ball on the fly, in my mind, the only other really promising option is to go with the passive catch, where the hand is just kind of ready, it's like low stiffness, and the ball will just come in and be received. But as we talked about last week, that's really hard to do with these balls because they're so light and they don't really have enough inertia to like get the hand moving. Yeah, so there's a bit of a trade-off here. And actually, there's one aspect to this that I haven't really mentioned before, which is definitely worth mentioning. And John has proposed this as a one reason as to why using this pre-calculated trajectory is a helpful thing to do, which is that after the ball is caught, if we use a passive catch approach where the hand is just set up as like a spring and the ball comes in and it's just like gently passively received, unless we can very precisely tune those parameters to make the hand be appropriately springy, if we can't get those like spot on perfect, then it's fairly likely that the hand will end up in like the middle of the stroke. It won't be right at the bottom of the stroke. It'll be somewhere between the top and the bottom. And to be honest, we probably want to err on that side because we don't want the ball to be like smashing the hand to the bottom of the stroke every time we catch. So we want to err on the side of having the ball finish kind of like in the middle of the stroke, which is a problem for when we then want to catch. Of course, the whole way the juggling works is you catch and then afterwards you have to throw. And to get the throws to be as gentle as possible for the hand, we want to maximize the amount of the hand stroke that we use during that throw. So we want the hand to be right at the bottom of its stroke before we make the throw so that we can use that whole stroke length. But that means that when we do the catch, it has to finish at the bottom, which is why this pre-calculated trajectory is really handy because it will always end up right at the bottom of the stroke. But we need to get the timing to be perfect. The timing has to be really, really spot on. So, yes, we'll see how well that will hold up. Let me actually grab as well. I want to show you my dropper. So let me just grab it. I don't want to carry the whole tripod over here because getting that positioned correctly took quite some time. So yeah, what this looks like is a little U-beam thing, and I've got bolts here with lock nuts on them to keep them kind of the same in the same position, and also to make it so that the contact area to the ball is a little bit bigger than just the bolt head. And this just grabs onto the ball, and then when it's time to drop, I can just like pinch these two arms at the top and it drops out. But unfortunately, it doesn't always drop out super reliably. Like if I don't know, if I like pull one side more than the other, then it will like kind of like come out like this sort of thing. Obviously that's not that extreme, but yeah, it's not perfectly reliable. And getting it positioned in that in the same spot every time, because like this can grab it like off to the side, or it can be a little bit higher up as it is here, and like this is a bit spinny now. So like yeah, it's not ideal. I probably should actually just like print little caps to like replace these lock nuts so that I can like grab it a bit more repeatably. I think that would be a good first approach to make this better. But all this to say, if anyone's got any ideas for how to make a good dropper that is reliable, and also ideally one that I can actually activate from a distance so I don't have to walk over there every single time to trigger it, I'm all ears. I would love to see what you guys come up with. To get this, I just like looked around on Google for a bit to see what other ball droppers people had made, and found basically this design that someone, I don't even remember why they made it, but yeah, I found this, and it works. It's good, but it's yeah, definitely not perfect. And unfortunately, I haven't been able to find any. I follow the Wintergarten project, which I'm sure many of you do as well. The like marble machine, and he obviously has worked with dropping marbles on balls a lot, but I don't know. I haven't been able to like directly take any of his ideas yet. They seem like they're a little bit more involved. Yeah. A little bit difficult to like directly copy over for my application. But yeah, if anyone's got any ideas, I would love to know. Yeah, so interesting week. There's still more to do with this to figure out, to get to the bottom of why this timing is weird. But yeah, right now, I'm not sure how I feel about it. I have faith that this can work, and like the motion capture is tracking at 300 frames per second. It is very precise. Like right now, I just did a calibration yesterday, so my error, my residuals are like, they're all less than a millimeter. So it should be good. It should be very precise. The timing should be able to be spot on. So I don't know why it's not. Yeah. Cool. There is one other thing actually that I want to mention, which someone had the suggestion of doing this last week. So last week I mentioned that we have a problem, which we can see right now actually, where when the ball is in the hand, so we can see right now the ball is down in the hand. Let me actually show you this view as well. Sorry, that one. Yeah, when the ball is in the hand, especially when it's down at the bottom of the stroke, the carbon fiber tubes that make up the frame of the arm, or like the platform part, tend to bisect the ball, and the tracking software seems to like splitting this into two. And I was talking about this a little bit last week, so if you're interested in, I don't know, how annoying this problem is, you can go back and look at last week's stream. But what I want to say now is that there is potentially a way. Someone's suggestion for this is that if I was using traditional like computer vision approaches for this, then you can do a thing called dilation and erosion, where, like, let's say if I'm trying to look at this ball, if I want one way to pre-process the data before I like fit a circle to this ball, one thing that I can do is we can dilate the area that we think the ball is in, make that a little bit bigger, like expand its size, basically like blur it out, and then we apply a round of what's called erosion, where we just like cut away that blur. And what this can do is if I have like, for whatever reason, I have like a little corner of this ball is like knocked out for some reason, like I don't know, if we've got like black tape on this that's like covering up a little bit of it, then when we dilate and erode, and especially once you do this a few times, it just like gets rid of any of those sort of like partial cover-ups. So you dilate it out, you make it really large, and then you just like crop it back down again. And it doesn't, if you're just like thinking about this for the first time, it might seem like it's like, why does this work? This seems a bit weird, but it does. And this person, I can't remember your name, sorry, I apologize. But they were suggesting I could potentially use a dilation and erosion approach to fix this problem here, because right now we've got the ball is being bisected, but if we dilate what we think the ball is, then we can dilate it enough that it covers up that blocked section, and then we can erode the edges, and it will still stay as a sphere. It'll just be one single sphere. Unfortunately, I cannot add any custom processing steps into the pipeline of like tracking these balls. It's like when these cameras are looking at this ball, I can't do anything with like this circle here. So like if I look at this camera, I can't change anything custom. I can't write custom code that will affect this tracking. And I think that's kind of fair that they don't let you do that, because this system needs to run extremely quickly. And I think if they started allowing people to run custom code, then the people who were doing that would say, oh, or some people would say, oh no, my system's running really slow. I've got lots of latency now. And it's just their fault because their code is not optimized, which is certainly what mine would be like as well. However, there is this setting in here for the marker threshold. And let me actually bring this back up so you can see it. Yeah. So we can see on the side here, there's this marker threshold thing. And let me actually show you something quickly. So one reason why I always have that screen down is because those tapes up on that shelf there are retroreflective tape. And the cameras, most of them, can see everything except for this camera, can see those tapes, and that just confuses the system. So it thinks that there's markers up there when there actually aren't. But the reason why I'm pulling this up now is because we can use these to actually, so I can show you what this marker threshold thing does. So if I increase this threshold, I don't know the proper way to describe what this is actually doing, but it's basically, from my very layman's understanding of it, it's allowing for the marker to be smaller and like more segmented. So like if it detects like tracking data here and tracking data here, if there's a low threshold, it will say, yeah, they're probably just the same marker. But if there's a really high threshold, it will like have very tight boundaries between when one marker starts and where the next marker starts. And so if we increase this threshold, we can see that it actually does, for some of the cameras, it does segment those tapes out into individual tapes, or like individual markers, which is what they maybe should be interpreted as. Versus if we have a really low threshold, it just kind of blurs them all into one. And we can see on this like intensity view, oh no, I didn't want to change that. What was that before? I don't know. Let's say 80. I'll fix it later. Yeah, so as we change this threshold, we can see that it handles all of those tapes differently. And the thinking is that, like, okay, maybe if we just have a really, really low threshold, maybe this ball being bisected can end up being observed as one ball rather than two. So we can see, like, this camera in particular is seeing, this is the ball in the hand, so you can see it in the intensity view. Yeah, this is a very good view actually. So we can see exactly what's going on here. The ball is just being cut by this tube. And if we change this threshold, we can get pretty close to having a full ball. Like, look, that's so close. But unfortunately, this doesn't let you go less than 10%, and so I can't actually get it to be fully a ball. Although maybe changing this exposure time, yeah, there's a bit of playing around that I need to do with this software. Like, I don't know, there's a tricky balance between learning the software that I have here. So that's actually much better. Yeah, between learning the software that I have and like getting really, really good at it versus just like moving on with the project. And like, yeah, this software can definitely do a lot more than what I am using it for. Let's try this actually. So I've just increased the exposure and flash time, which is like how long the cameras are receiving light for. And this means that they should be getting more crisp signals from the markers that are actually markers. But it also means that there's going to be more noise in the system. So we can see like this view here, there's all of these things. Like, I don't even know, what is that? Let's have a look. So the intensity view kind of shows the That's the tripod. Okay, so the tripod is coming up as a marker on this camera. But let's see if that... Okay, that has actually helped. That's very handy. So increasing the flash time and decreasing the threshold means that now this ball that was previously bisected into 2 is now 1. But it means that there's also more noise. So if I can be really careful and make sure that there's like nothing that's remotely reflective in my space, then this should fix that problem. But if I can't be sure of that, then we will have this bisecting problem. This is interesting. This is good. I like this. Yeah, so whoever that was, whose name I cannot remember off the top of my head, thank you for suggesting this. But yeah, look at all these. Like, what is this? This is like directly above Jugglebot. Oh, it's the tripod again. Yeah, okay. So yeah, I think I need to just go around and cover everything that I own that's kind of reflective in tape. Like masking tape. But I guess that maybe will solve the problem. That's good. Anyway, yeah, so there's lots of things going on, as always. And as always, I hope you found this interesting. I believe that's everything for this week. I believe there will be a stream next week. I need to check my calendar more before I start doing these streams, but I'm pretty sure I'm not doing anything next Friday. Yeah, if you've got any thoughts on any of this, I would love to know. Especially the timing stuff. That is my biggest, I don't know, concern right now. But yeah, any thoughts are welcome. Yeah, there's a couple other things to say, but I'll wait for when they're more relevant. Cool. All right. Good luck with everything you're doing, and I will see you next week.